Hi, my name is Alex Fleischman, and welcome to the video overview for the electric field demonstration. This demonstration will introduce students to how a buildup of electric charge can result in a net electric field. This electric field can induce motion on a free-moving metallic object. The goal of this demonstration is for students to induce motion on a free-moving metallic object due to an electric field. Let's begin our approach to this problem by analyzing the Wimshurst generator. As we rotate the crank, electric charges build up on the little metallic heads. The charge buildup results in a spark across the two heads to, in quotes, relieve the force of attraction between the two stationary heads. Let's look at a visual representation. As you can see, there's a positive and negative metallic head. These two heads are stationary. Due to the positive and negative charges, there's a force of attraction between the two heads. However, the two heads cannot move. Therefore, the two heads create a spark in between themselves to, in quote, relieve the force of attraction between them. Now that we talked about the Wimshurst generator, we must connect the charge heads to a plastic plate using alligator clips. This connection will allow charges to transfer onto the plates and disperse uniformly. A representation of what's happening on the plates can be seen below. The key part in this demonstration is to note when the two plates face each other, an electric field is created. It goes from the positive plate to the negative plate. So what would happen if we place a free-moving metallic object in between the electric field? Well, it would start rotating. Now let's go over why the free-moving object moves. Let's take the electrons on the right side. The electrons are negatively charged and are very close to a negatively charged plate. Therefore, there's a very strong force of repulsion between them, and there's a slight force of attraction between the positive plate and the electrons due to the far separation. This will induce a slight rotation, but now the electrons are on the top, so they're experiencing a medium strength force of attraction between the positive plate and a medium force of repulsion between the negative plate. Now we have electrons on the very far side, very close to the positive plate. They're experiencing a very strong force of attraction. However, this is happening at each end, so there are electrons on the opposite side who really don't want to be close to the negative plate. Therefore, it continues its motion. Now the electrons are on the bottom part of the free-moving object. They're experiencing the same force of attraction and repulsion as they did when they were on the top part. But note, this is happening as a cycle at every single end of the free-moving object. Therefore, it will continue its motion. Let's continue. What would happen to the free-moving metallic object if one plate was angled? Note, it's not perpendicular with respect to the other plate. So what would happen to the free-moving object if one plate was set perpendicular with respect to the other plate? Well, the speed of the object will decrease until 0 meters per second. This is due to no electric field being present when two oppositely charged plates are set perpendicular to each other. Let's review. Two oppositely charged plates will create an electric field between their separation. When one plate is angled, the electric field decreases in strength. And when one plate is set perpendicular to the other, there is no electric field.